Okay, so let's look at kinematics in 2 dimensions. We shall look first at acceleration. So we shall be looking at acceleration of an object first in 1 dimension. And since we are interested in 2-dimensional motion, we shall look at both the vertical motion and the horizontal motion. Let's start off by defining average acceleration, A average, and this is defined as the change in velocity divided by time. So we can write A average equals delta V divided by delta T, where delta V is just V final minus V initial, and the delta T is T final minus T initial. So we shall look at the motion of an object that is moving along a certain trajectory, and I've drawn a trajectory which we shall look at next. So suppose we have an object moving with the following velocity vectors, where I've labeled V initial and V final. We can find average acceleration by taking the change in velocity vector divided by the time. So with our change in velocity, we just subtract final velocity minus initial velocity. And so I've just taken those 2 vectors, V final and V initial, and I'm going to subtract them using a vector approach. So what you see here then is I've taken the final velocity minus initial, and I've taken the initial velocity vector and I flip it over and add it to the final velocity vector as we've learned before. Then I draw and I take the tail of the initial velocity vector and put it on the tip of the final velocity vector. So the change in velocity is the arrow drawn from the tail of the final velocity to the tip of the initial velocity. That change in velocity vector gives us the same direction as the acceleration average. So what we have here is a vector representation of average acceleration. Since A average is a vector, we will later take the components of acceleration, so we can break acceleration into the x component and the y component. And we will do that in section 2 of section 4.2, which is 2-dimensional kinematics. So I've drawn a few trajectories below for an object moving in the xy plane. And so you can see that I've drawn an arrow from the origin to a point along the trajectory, and that is an arrow that represents a position vector for that point. And that position vector has the notation r, vector notation r, so a component of r is rx and ry, shown on the trajectory on the right. Rx just represents the x component of the vector r, and ry is the y component. So the vector r can be written in unit normal vector notation as rx I hat plus ry j hat. So now look at this xy plane that I've drawn. So the trajectory of the object in the xy plane is shown where it goes from position 1 to position 2, and I've drawn position vectors to position 1, which is ry, and a position vector to point 2, which is r2. And so the change or the displacement delta r is just r2 minus r1, or we can say r2 is just the r1 plus a certain displacement delta r. So this implies again that the displacement of the object is delta r. So using our definition for average velocity is just displacement over time, and so in unit normal vector notation, delta x I hat over delta t plus delta y j hat over delta t will be the average velocity vector. Suppose we wanted to find instantaneous velocity for this object. We can define instantaneous velocity in the limit as the time is shrunk to 0 of the average velocity. So this just tells us that the instantaneous velocity v is just the derivative of the displacement vector d dt of delta r, or dr dt. So in the xy plane, we can look at the instantaneous velocity vector below by thinking of the three positions 1, 2, and 3. And the 3 is the widest displacement. Suppose we just shrink the time interval from 3 to 2 to 1. This will imply that we are making the delta r very small, so we are actually shrinking the time to a given point. And so at that point where we have a tangent to the trajectory or a tangent line to the curve, that will be your instantaneous velocity vector. So if we draw that instantaneous velocity vector on the trajectory in the xy plane, you will see that the x component v subscript x is v cosine theta, where theta is the angle between the vector and the x-axis. And so we see Vy is just V sine theta. So the instantaneous velocity vector has the two components along the x and y axis. Once we know instantaneous velocity or average velocity, we can next look at the acceleration from our velocity vectors. Suppose we have the trajectory again shown in the xy plane where the object is at a certain point V initial, and then a certain time later, at the time delta t later, it will be at a point 2 v final as shown on the trajectory. The change in velocity vector just leads to an acceleration which points down towards the x-axis as shown on the right xy curve. And since we've done this a few times, I didn't go through and show you how this is done, but I think you know how to do it because we've done it multiple times. So I'll draw a new trajectory showing you the acceleration described on the curve. So with that acceleration vector A, we can have two components, an x component which is parallel to the x-axis and a y component which is parallel to the y-axis as shown there. Since acceleration is a vector, we can now see that the magnitude of acceleration, so what I should do is take the vector notation off of this. So the magnitude of the acceleration is just given by the square root of ax squared plus ay squared. And in unit normal vector notation or unit vector notation, a subscript xi hat plus a subscript y j hat is just equal to the acceleration vector a. So now that we found the x and y components of acceleration, we can now write our full kinematic equations in 2 dimensions by writing the kinematic equations along the x-axis and then along the y-axis. So I've written them out. So x final is x initial plus v initial x delta t plus half a subscript x delta t squared. So that will be the final position along the x-axis work for an object or let's say a particle that is moving along the x-axis with an acceleration a subscript x, initial velocity x, v subscript ix, and an initial position x subscript I. The final velocity along the x-axis will be given by v initial subscript x plus a subscript x delta t. And we can see the other formula for final velocity that you can use, suppose you don't have the time delta t. Now let's look at the kinematics along the y-axis. So again, we can write the same kinematic equations. We've just replaced the x letter with the y letter. So y subscript f is equal to y initial plus v initial y delta t plus half a subscript y delta t squared. And the rest of the formulas follow as before. Let's look next at an example. So in this example, an aircraft moves in such a way that its acceleration is given by the vector a equals 3i hat plus 4j hat. If it starts from rest, find its displacement and final velocity after 20 seconds. Let's assume that its initial position is 0. So I've given you all the necessary information to do this exercise. We are thinking of a displacement. We're looking at a displacement delta r. So let's give you a few minutes to do this. So after you've spent a little bit of time working on this, the answers that we have are the displacement delta r is 100 meters and the velocity v should be 100 meters per second. Those are the answers that I have received. Let's check if these answers are correct. So I'm going to put a square around them and say, let's check them. Okay. So let's take out the things that we know. So initial position r subscript I is equal to 0. So taking that in component form, x subscript I is 0 and x final is also 0. No, that's not right. So we are just assuming the initial position is 0. So that tells me that x initial is 0, y initial is also 0. Okay. I'll remove this portion here. Okay, so using the x components first, x final is shown there. The formula for the x final or final position is x initial plus v initial delta t plus half a subscript x delta t squared. Our delta t is 20 seconds and our a subscript x or x component of acceleration is 3 meters per second squared. So plugging this into the x final equation, we have x final equals 600 meters. So that's our final position in the x direction. We can now find our final position in the y direction by plugging delta t equals 20 seconds and a subscript y equals 4 meters per second squared. We already know that the initial velocity is 0 and the initial y position is also 0. So plugging this into the y final formula, we have 800 meters for y final. So the position of the particle after 20 seconds, or the position of the aircraft after 20 seconds, is given by r equals the square root of x final squared plus y final squared. You notice that this is just our Pythagoras' theorem. So this is the square root of 1 million. If you just plug in those things that we have, 800 meters squared plus 600 meters squared, that gives you 1 million. So the square root of 1 million is 1,000. So our final position is 1,000 meters. Let's look next at our final velocities. So we can use our kinematic equations again. So the final velocity in the x-axis is given by v initial x plus a subscript x delta t. So just plugging in 20 seconds for delta t and a subscript x is 3 meters per second squared. We have the x velocity, the final x velocity, which is 60 meters per second. Final y velocity is found the same way. We plug in acceleration in the y direction, which is 4 meters per second squared, times delta t, which is 20 seconds. So the final y velocity is 80 meters per second. And so since velocity is a vector, our velocity magnitude for this aircraft is the square root of vx squared plus vy squared, which is 100 meters per second. We can next find the direction of the displacement and velocity vectors. And since the displacement vector will lie along the same direction, or since the displacement vector determines the direction of the velocity, once we find one, we know the other. So we use our formula for theta, which is tangent inverse of ry over rx, and that gives us 53.113, 53 degrees approximately. So this would be the end of our kinematics in 2 dimensions.